Alright, we stopped on trees, and now we are continuing with graphs. I have here a nice little centerpiece, mind map for the graphs, and now let's talk about some theory about it. So basically, if you remember from the last episode where we did trees, if you didn't, I'm gonna probably link the episode somewhere, but if you remember what a tree actually is, it's a type of graph. But not all graphs are trees, and what a tree is a graph but without all the cycles. And simply put, a graph is nothing more than a collection of nodes with edges between some of them. Now, there are some classifications of graphs like directed or undirected. Basically, the difference between a one-way streets or two-way streets. I think this is also a good distinction to make. And how could we draw a graph? Probably like this. I'm so wobbly. Let's say this is a simplistic example of a graph. So just to hit the nail on the head, basically what we have vertices or nodes, which are vertices or nodes which are entities in the graph. And these are the numbers here, and they can represent, here we represent simplistic numbers, but they can represent mostly all of modelable data, like cities in a map, people in a social network. We have edges, which are relationships or connections between vertices, which are these arrows between nodes. And as I said, we can have directed versus undirected graphs, those who have directions. I don't know, difference between directed and undirected graphs are Twitter, where you can only follow one user without the user having to follow you back, or Facebook, or undirected graph, where we have friendships that are mutual. Also, we can have weighted versus unweighted graphs. Maybe I could also add that here as well. Sparse versus dense graphs, but I think for now we are gonna stick with the basic. We're gonna do this, and probably we're gonna mention some other concepts as they come. So what is the most common way to represent a graph? We can represent it by creating a class of graph, which would have an array of nodes. And each node would have, now let's also create a class of node. And each node would have a name and a list of its descendants or children. I'm also gonna put this here. Now, the difference between a graph and a tree is that in a tree, from a single node, you could most probably reach all the other nodes. But in a graph, that's not always the case. So we have two ways of representing, as I said, representing a graph. We can represent it via adjacency lists. Or adjacency matrices. So the difference between a list and a matrix is correct. So I was talking about adjacency lists and adjacency matrices. So these are, as I said, two common ways to represent graphs, and each has its own set of disadvantages and advantages depending on the operations you need to perform and the type of graph you are using. But basically, a list is a collection of lists or arrays where each list corresponds to a vertex and contains the vertices it's connected to. So for something like this, let me also reduce this a bit. So what do we have? If we have something like this, A is connected to B, and if we have something like this, so how could we represent an adjacency list? We can represent it like this. A is connected to B and C. B is connected to A and D. C is connected to A and D as well. And D is connected to B and C. So some of the disadvantages of adjacency lists is that it's space efficient. So because it only stores edges, it uses much less space for, I don't know, bigger graphs. It's efficient. Now we have a slow edge lookup. What does it mean? It means if we want to check if an edge exists between two vertices, it can take a lot more time to check for it. Now, what's a matrix? A matrix is a 2D array where each cell, so we will have cells I, J, where each cell will indicate whether there is an edge between the vertex I and vertex J. So if we have the same graph as we did for the adjacency list, we can write probably something like this. A, B, C, D, and the same thing down. So A and A didn't have any connections. A and B had one. A and C have one. A and D don't have any. B and A have one. B and B don't. B and C don't. I think the same thing happens here. We have this is basically an adjacency matrix, and it's really fast. Checking if an edge exists between two vertices is, I think, instant. It's easy, simple to understand. I think it's basic, and it's good for dense graphs. Now, the disadvantages of adjacency matrices are that it's really space inefficient. Compare just the size of the list and the size of the matrix, and the space they require. So, nah. I think that's basically it when it comes to graphs. What else can I say about them? What else can I say about them? Yeah, I forgot. We have two common ways to search a graph, and the two common ways are depth first search and breadth first search. And we're gonna implement both of these. I'm just gonna write it here. So we have breadth first search, depth first search. What size is these? These are 10. All right, so what's the difference? We have two types of searches. We have depth first search and breadth first search. So in depth first search, we start at the root and explore each branch completely before moving to the next branch. Start, explore. And the breadth first search, we start at the node and explore each neighbor before going to any of the children. Oh, I can fit. Before children. Okay. So let me remove this. Let me open Visual Studio Code. No, not this. Yeah. So just to hit the nail on the head one more time to repeat this. So we have breadth first search and depth first search, and again, breadth first search starts from a vertex or a node. It visits all of its neighbors first, one level at a time, and then it uses a queue to keep the track of vertices to visit next. But the depth first search starts from a source node and then explores as fast as possible along each branch before backtracking, and then it uses a stack to keep track of its vertices. Yeah, we are using the stacks and graph and the queues again. And before we continue, let me just give you an example of how this works. So let's say we have this, 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 this. We have all of this. So breadth first search would start at A, then go to B, then go to C, then go to D, E, and F. But the depth first search would first hit. Okay, let's do this again. We start from A, we go to B, we go to D directly, like this. Then we go to E, and then we go to C and F directly. So this is the difference, and now we can implement both of those. So let's do this. I'm just gonna remove the blackboard. Class graph. Yeah, we are implementing a graph. We can initialize it. All right, so what are we gonna do? We're gonna do a list, adjacency list. I could also use a matrix, but let's use an adjacency list for now. So add vertex self. We are now gonna create some functions that generate graphs. So if we don't have a vertex, and why doesn't it allow me? So if we don't have a vertex in adjacency list, let's add it. This is simple. Let's add an edge as well. If we can't find a vertex in our adjacency list, let's add it. No. Nice, nice, nice. This should be the other way around. So a vertex 2 will be appended to no, pardon, vertex 1 will be appended to the vertex 2, but if we have a bidirectional graph, in that case, we're gonna do the same thing. Why am I not copying this? Only this time, like this. All right. This was the edge. So we created a method to add a vertex. We also created a method that adds an edge. What else can we do? Maybe remove an edge. All right, so what I'm doing now, checking if the first vertex is found in the adjacency list, and then if there is this vertex in the adjacency list, I'm also checking if vertex 2 is found under vertex 1 in the adjacency list. If it is, well, we can remove it. We're gonna do the same thing, but this time we are also checking for bidirectionality, and we are checking if vertex 2 is here, and if vertex 1 is found under vertex 2. Let's search for vertex 2 in our adjacency list and remove any notion of vertex 1. Okay, This was the edge removal. I think we can also do vertex removal. For this one, we need the vertex itself. So if it is in the adjacency list, what do we need to do? Okay, so if we have a vertex in our graph, we need to iterate. It's not simple only to remove the vertex itself. We also need to iterate through all the other vertices and remove any reference to this vertex. All right. So what is happening here? We want to remove a vertex. We check if it's found in the adjacency list, and if it is, we are iterating through all of the vertices we have for our vertex that we want to delete, and for each one of them, we are removing the reference for this vertex. And in the end, we just need to delete it. So basically, let me just show you what I mean by this. We have this pretty simple adjacency list. If I want to remove B, I'm iterating through the vertices that are under B, and then for each of these, I'm gonna remove B from their list of adjacency vertices. All right, what's left? Yeah, we just need to display it so we can have a better self. All right, I think that's it. Maybe neighbors, maybe I also can do this. So self and vertex. I don't think I need this, but let's do this. Okay. So how can I use this now? I can create, is this work? Will this work? Invalid syntax if bidirectional, and where line 24 and all right. So I'm gonna add a couple of those guys. And maybe also I could add D. So now I could add a couple of edges. So A will have B, A will also have C. Oops. D will also have both. Can I select it like this? Yeah. So it's gonna be D. And now I'm gonna copy the same thing again. But now I'm gonna have B that is going with A and... Oh, actually, no. No, I think this is bidirectional by default. So the only thing I need to do is this, I believe. And now if I do graph display, self, my bad. I'm referencing for some reason a function instead of... Why is that debugger on? I misclicked something, I don't care. So run. Yeah, nice. A has B and C, B has A and D, C has A and D has B and C. Okay, now let's create the two methods. For breadth first search, which will take a graph, it's gonna take also the starting node. So what we will have here? We will have a list of visited nodes. All right, so what we need to do? We need to perform a breadth first search on a graph starting from a specific node. And now breadth first search explores all neighbors of a node before moving to the next level of neighbors. So what we did here, we need to create a visited set because we need to track nodes that are already being visited or been visited. Let's create a queue. So the queue will be initialized with the starting node. I just need to add, if I'm not mistaken, a queue comes from a collection. So I need to add it here at the top. All right, nice. What else? We need to store the visited nodes. So how can we do this? Yeah, first of all, just to describe, just to explain the setup, we need the visited structure, because we need to prevent infinite loops in cyclic graphs. We need the queue that will be holding the nodes which will be added to the queue as they are discovered. And we need to ensure that nodes at the current level are processed before moving to the next level. And we have the result, which will store the order in which nodes are visited during the traversal. So while we have a queue, all right, we're gonna pop the first guy. Next, if the node that we popped is not in visited, we need to add it, right? Visited at node. What else? We also need to append this same node to the result. Next, we need to add new neighbors to the queue. For this, we have the extend graph node, and I think that's it. We just need to return the result. So now if I do print bfs graph, and what do we have? We have a. Why is my graph object not subscriptable? What? I think I should move this to... Should I move this? I think I need to move this in the class, most probably. So I can do this here. But here, instead of a graph itself, adjacency list node, and I think now I can do this. I don't need a graph here, right? Yeah, I don't need a graph here. And if I start from A, B, C, D. All right, let me just something that's, let's say, more complex than this one. Something like this, maybe. So all right, I'm gonna add B. B is connected to D. B will also be connected to E, and our C will be connected to F. I'm also gonna add two new E and F. So run all A, B, C, D, E, F. Yeah. So what this method basically did is that we explored all vertices at the current depth before we moved to the next depth level. We used a queue, so the first in is gonna be the first out. Because we are using the breadth first search, we are going level by level. And that's it, I think. Interesting. Hey, Seth. Thank you so much. Good luck to you too. Thanks, man. Alrighty then. Let's also create another one for depth first search. So self node. What else? I think that's it. We're gonna do the same thing. Visited. I'm gonna create a new set. Result. I'm also gonna create a new array. Now, what should we do here? Look at this. Let me just open this again. Yeah. So what we need to do here is hit one node, hit the main node, then hit the next one, then hit the next one all the way to the end, and then we come back. So how can we do this? if the node is not in visited, I'm adding the node. I'm adding it to the result as well. And then for each neighbor in self adjacency list for this node, self all right neighbor. I need to copy this. Why can this hit? It's not defined. Why is it not defined? Why is DFS not defined? Mm-hmm. Okay, so now we need to implement the DFS in the context of the graph class. So command why is it? I know what I need to do. I know what I need to do. I'm gonna do the same thing but inside this method, and I'm gonna call this DFS recursive. Here I'm just gonna say DFS start and return result. Not start, but node. Will this work? I have an error. Where's the error? What's the error saying? Wait, this should also be a start. Here it's okay to have a node, and here it's okay to have start. Can I run all of this? No, it still doesn't work. Yeah, of course it doesn't work. I didn't do anything. Why? I don't need a self here. Oh god, no. Yeah. Damn. Let's do the same thing. DFS, but this time iterative self. We're having a start. We're gonna do the same thing. It's gonna be pretty simple. I'm gonna have visited. It's gonna have a set. I'm gonna have a stack. That's gonna have a start first. I'm also gonna have a result, which is gonna be an empty array. Then, while we have a stack, we're gonna pop this node. And we're gonna add it to the visited and to the result. And then we need to add the neighbors to the stack, and we need to make them reversed. So this is gonna be self adjacency list of the node, and then I'm just return result here. Okay, fine, right. And I am, hopefully, no, I'm not. Add, because it's not add, it's append. Add I'm using for the set, and append I'm using for an array or a list. Oh god, oh god, oh god, something something took some time. It took some time because if the node not in visited, only then I'm using all of this. That's why we had an infinite loop. It's not a node, it's start. It's start, it's not a node. What? Okay, interrupt. I think this needs to be up. And then I'm popping it. And I think now it should work as it should. No, it doesn't. Why? Iterate. Okay, so I have a set of visited nodes. I have a stack that has only start on it, and I have a result. So while the stack exists, I'm popping one guy. So if it's the node, it's not right. Okay, simple. A round of applause for us. Thank you for watching. I'm gonna need to end it here early. I'm going for a movie, and I'm gonna continue next time.